Hello everyone. Wow, I see people are still flooding in, but let's start. So, as Rafael said, my name is Mateusz. You can call me Matt, that's completely okay. Originally I'm from Poland. Yes, don't worry, I'm used to people butchering my name. I've been living in Tokyo, Japan for 6 years, and I've been working with H2O AI for around 3 years now. And recently I started working on our machine learning interpretability module. And today I'm actually going to take you on a journey. And we will start with a very short story. I cannot really see anything because of the great light, but I will need a really short raise of hands to see, does anyone know what LIME is? L-I-M-E. Okay, so you all know this story because this story is basically from the LIME white paper. So LIME is this guy, imaginary guy in my head. Yes, I have some of those. Otherwise, I wouldn't be able to work at H2O. And he wants basically to create a classifier. So he gets all the data he can, like a whole bunch of images. He does his data science-y stuff, ingests the data, cleans it up a little bit, right? Builds the model, and uses the model for predictions. And it's awesome, because LIME is a good scientist, or he used driverless AI. It's so good that actually he gets only one mistake out of the whole validation data set. But is it really that good, right? Like LIME is showing it to his friends, and the friends are saying, okay, this is really cool, and they are starting to ask, how does it actually work? And he starts to think, right? So he starts to investigate, and what he sees is this, that he just created the world's best snow detector, right? But what he actually wanted is like a detector between whether it's a wolf or husky, right? But what the machine learning model actually learned is that usually when there's a wolf in the picture, in the background there's snow. When it's a husky, right, in the background there's a lot of grass. And you can see it clearly here, right? On the first picture, when it predicts wolf, there's a lot of snow, and that's what it shows what the machine learning model used, right? With husky, you see the grass and only the part of the husky that looks like grass, etc., etc. And the only one that actually was wrong was a husky on a background with snow, right? But then again, LIME is like, okay, so what? There's been a lot of, companies that wanted to do one thing, but then they pivoted, like Not Hot Dog, for example, which was bought by Twitter, if I remember correctly, in the series. So why should I care, right? Well, the problem starts when your models literally can kill people, right? Like, for example, you're working on self-driverless cars, right? Or something very similar. Even if you're doing predictions in banks, etc., right? This all has direct impact on people's lives. What if you need to reassure your stakeholders, like clients, bosses, etc.? What if you need to debug your models? Like, how do you do that? Like, if you're in a really regulated industry, like banking, how do you actually show the regulators what was your reasoning behind it, right? So the first thing we need to actually talk about is what is machine learning interpretability, right? Because whenever you will go to people, like everyone will tell you something different. Like for different people, machine learning interpretability means something a little bit different. So for me, the basic idea is that you don't really care about the inner workings of the model itself. Like, I don't really care what the architecture in deep learning that I'm using is, as much as like what is the relationship between the input, right, and the output. Or to say it in different words, if I would have children, like 5-year-old children, and I would put them in front of the computer and they started to ask why, like my perfect explanation is exactly when they start asking why, because they don't have any more whys, right? And it sounds good, right? Like we should be doing it. Why not? It's only benefit, right? Well, the problem is that intrinsically, machine learning models are using high-degree interactions between your input features. And sometimes it's really hard to actually disassemble them into interpretations on every single column or feature. It's usually like there's really very few cases where it's completely impossible, but sometimes, especially with deep learning and stacking, well, getting to the source can be really challenging. The other problem is that usually for a problem, there's not one single best model, right? Unless it's a linear problem, like on the left side, you will probably have multiple best models, right? Multiple maximums. And the problem with that is if you train them, as you train with different seeds, your explanations will also be different. And this is more of a problem with a human mind that people will not trust that. Like if your explanations change for different models, even if it makes sense for the new model, like you will be suspicious of it. The other problem is with scopes of interpretability, right? So there's a few ways you can do it. You can interpret the whole model on an average basis, but that can introduce some issues like noise when you average out all your predictions, etc. So what you usually want to also do is local interpretations, right? So you have to implement both. And by local interpretations, I mean you want to interpret a single observation. For example, when you're doing a credit score machine learning model, you want to be able to say, like, why this person has this kind of credit score, or why this person will default exactly this one, right? Not the model as a whole. And another problem is, like, there's also a lot of several types of interpretability. You can do interpretability on your specific model, which is usually the best kind of thing you can do, because this is exactly targeted at this one model. But the problem is, what if you want to incrementally change your models, right? The method you've been using at the previous step will not work for you, probably in step +1, right? So what we came up with, well, what we are using is model agnostic methods. So methods that don't really care about inner workings of the model, and you can actually run them on any specific model. The problem with those is that usually they are not as accurate, right? So there's this problem between high fidelity, so yes, I can really trust you with a high degree, or low fidelity. So this was like enough of the introduction. Let's go into like how you can actually interpret the whole thing. So personally, when I talk about machine learning interpretability, I start with the data. Like before you even start doing any modeling, etc., you should look at the data. And one of the things you can look at is correlations between different features in the data set. One example of a myth that has been pretty popular recently in the news is the Amazon recruitment AI. If you've heard about it, they had a huge problem with bias in the sex column, right? Like apparently their AI was trying to choose really a lot males for recruitment. And that's because the sex column was highly correlated with other features, right? So the machine learning model learned exactly that correlation. If you look at your data set and you see that like certain columns don't have that kind of correlation, then it's okay. If you see that they do, like you can, even before you start modeling, do something about it, right? Like you can, for example, ignore that column or do some kind of transformations. You can obviously work with what people call white box models, right? So those are models that can be easily interpretable by themselves. For example, linear models, logistic regression models, decision trees models. With linear models, it's easy. You take only the coefficients, right? And those are what we call reason codes. So the reasons why we did such and such prediction. With decision trees, you can literally print it out and show why was the path to the actual prediction. The other thing you can do is you can actually visualize interactions in your models using things like partial dependence and individual conditional expectations, which are pretty similar things. ICE is for a single model, for a single row, so it's a local explanation. PDP is for the whole thing, so a global explanation. So how this works is you basically take your model, you take your data, you choose which feature you want to check how important it is, and you generate a set of values that you want to check for it. So you run the prediction, changing the value in that column on all the data, and you average it, and you see how the predictions change. If the prediction changes a lot with only a small tweak, that means that probably this feature is really important. So this is from driverless AI. We do have an MLI module already implemented, and this shows on the yellow line the PDP for a set, and on the gray lines are the deviations, whereas the white one is the ICE. So another thing you can do is sensitivity analysis, for example, residuals. And how this works is you basically generate new inputs, either randomly or you think about it, what can happen, and you just throw it at your models. This is really important. This kind of random attack model attacks are really important on production models because you most probably won't be able to figure out all the inputs that actually will come from your production space. And this basically shows you how sensitive your model is. If the changes are really big, this probably means that there's something wrong with it, and you probably don't want to put it in production because you will have some issues. Another thing that a lot of people have problems figuring out at the beginning, because it is a little bit mind-boggling, is this notion of a surrogate model. And basically, it's a substitute model. This is really correlated to the whole high fidelity and low fidelity concepts that I was talking about before. So the models that usually you create are very complex, but you have high fidelity in them, right? So a surrogate model would be a low fidelity model, so one that you don't have as much faith in, but are much more explainable. So usually, this is a prediction of your prediction, but you can actually show it visually really easily. So one way is the decision trees that I was talking about before, right? This is a white box model, but a surrogate. Another thing is this thing called LIME, Local Interpretable Model Agnostic Explanations, which tries to cluster your data set and predict a GLM for each cluster and uses those coefficients for each observation. The state of the art nowadays is Shapley explanations. So there's a few ways to generate feature importances. Usually we were using stuff like Gini, metrics, etc. in trees, and that's pretty cool, but it has some problems. First of all, it shows you only the absolute value of the importance for each feature, right? So you don't really know if it's a positive or a negative impact on the prediction. The other problem is that the math is there, but it's not like super sound. So with Shapley, which uses game theory, there's a lot of math showing that, okay, those explanations actually make sense, and we are really, really confident in how this model predicts. The other good thing is that they actually show you the signage of the feature importance. And with feature importance, you should be doing both the global feature importance, so like here, and local feature importances. So as I said, per row. So a few best practices to consider. Well, first, consider deployment, right? This is something that we talk about a lot in H2O ourselves. You know that we have this whole concept of a Python pipeline or POJOs in H2O3, or what we call modules, which are basically Java binaries in driverless, right? So for us, it's really important. Like, if we are not able to give you something like that, it's useless, right? It's the same with machine learning interpretability. It doesn't matter if you have like the world's best model, if you cannot deploy it, and if you cannot interpret it at runtime, right? This was the problem with the original Netflix prize, right? The $1 million reward. Even though someone came up with a really great idea and with a really great stacking, like they didn't really implement it in production because it was so complex. If you can, just train a monotonic GBM and use Shapley values. Usually that's everything you need, and it's really good for explanations. You should, as I mentioned many times before, you should use both local and global explanations, because global explanations are awesome, but as I said, noise, not good. And there's actually a few examples that we have online showing that the local explanations are completely different than the local ones, and we try to explain to you why is it like this. Sensitivity analysis with random attacks is really important, and please test your stuff. Like, this is something I cannot really reiterate enough. Like, you have to test both your models and the software that you're using. Don't really believe in stuff without testing. Model-specific explanations are awesome, and well, you have to beware of uninterpretable features. And by uninterpretable features, I mean not features that literally cannot be interpreted, but features that are really hard to interpret, you know? So yesterday, we actually uploaded on YouTube, on our YouTube channel, a 1-hour walkthrough by Patrick Hall, who is the brains behind like, the whole MLI package. Like, he's one of the professors at George Washington University in Washington. And he's been working on MLI for like close to 5 years now, and he designed everything that we actually implemented here. And this is very slow, very meticulous, and shows every single piece of the MLI package. And Patrick is really good at explaining why each piece is done like this and why each explanation looks like this. Because usually this is a really new field, right? So it's really hard for us to say, okay, just give you a bullet list saying, okay, you do this, 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 and this. This is still a little bit more art than science. And you actually need to know like that you can use decision trees and, for example, PDPs to find correlations and how to do it. So we also have this MLI resources GitHub repository where we try to collect all the booklets, all the white papers, all our presentations, et cetera, et cetera. So this is a really good place to start if you're just a beginner. Yeah, I can show a demo unless we have a lot of questions.
Do you have questions?
Okay, then let's do that. Okay, thank you. Yeah, okay, so the first question is, if you don't have complete introspection into how an AI model works, how can you stop it learning unethical biases which may be ingrained in historical data? Yeah, this is a really good question. And in the MLI resources, we have one paper on bias, which you definitely should go and check. There's a lot of ways to do it. Like, for example, you can look into your data sets, and for each feature, you can check what's the distribution of predictions. If for certain groups, the distribution is completely off, that might mean, for example, that there might be something wrong, or that we screwed up a little bit with the data. So this is one way. But there's like a whole white paper if you want to check it out more closely. Are there any plans to add Lime to H2O open source product? We're thinking about it. So actually what you've seen is the Lime that I've shown on one of the previous slides. This is already implemented in H2O3. So we're on the back end, we're using H2O3 for this. So we're thinking about it, we're talking with our CEO, we'll see. What else? In your opinion, what's the best model agnostic interpretation technique? Shapley. The problem with Shapley is that it's model agnostic, but you still need to know a little bit about the model. But in theory, you can run it on anything, and that's what we're trying to implement nowadays. Why Shapley? Because there's concrete math behind it. I'm not an artist personally. I need an equation and someone to come to me and tell me exactly why this is done like this. This is my biggest problem with previous feature importances like Gini, etc. It's like it's kind of shaky, you know. Some math is there, but it's like it doesn't always have to add up. What else? How do you test models? I'm guessing the models themselves. So one thing you can do is the sensitivity analysis, right? So for example, on this slide, right, what you do is you generate completely random observations from your feature, from your space, possible space, and you throw it on your model, and you plot it, and you see what are the differences in the predictions. Like, for example, here on the left and on the right, the difference is really huge with really small tweaks to the data. This probably means that that's not what you really want. This is probably some bug in your model. This is one thing to do. If you mean how do you test MLI, then go to O'Reilly. Patrick has a whole blog post on how to test machine learning interpretability. How do you manage interpretability with one-hot encoded columns where a column is exploded to many columns? Yeah, this is a really good question, and for now we don't. that's the short answer, and we're thinking about it because we definitely will need it for NLP. Can you say again the name of the professor who designed those amazing visualizations? I mean, he didn't really design them. It's Patrick Hall, H-A-L-L. He's working on machine learning interpretability, but he's not the creator of PDP, et cetera, et cetera. He just figures out what to use. Unless you meant the amazing visualizations in the AutoVis, that's Leland Wilkinson. Okay. I think we're done. Cool. Thank you.